Okay, my name's EJ Daigle, Dean of Robotics and Manufacturing here at Dunwoody College, and we're up to the lecture on S7-1200 timers and counters. So a little bit demonstration on the Siemens software using timers and counters. All right, first and foremost here, as we think about timers and counters, when we worked with like RS500 as an example, we were limited on our preset time for timers and counters. So when you notice the Siemens software, the preset time, although it can be entered in milliseconds, one of the beautiful things about the S7-1200 timers is that you can actually enter 9 seconds or 9 minutes or 9 hours. You can enter it however you like to enter it in there. So as an example, if you wanted to, knowing that the maximum value is 2,147,000,000 milliseconds, I could enter it as milliseconds, and just type it in as, instead of 9 seconds, I could type it in as 9,000 milliseconds, and that would be just fine. Unfortunately, I tell you, that's kind of not how humans operate. We don't say, hey, I'll meet you over at the bar in 5 million milliseconds. We'd much prefer to give them a time that, corresponds to a clock or a real human value. So that can be a little tricky, but not really, because if I want 9 seconds or 9.5 seconds, I can actually enter it as this, 9 seconds, 500 milliseconds. However, this also poses some issues when you're looking at the milliseconds or the elapsed time or something like that. You may want to actually be able to distinguish, well, if someone enters 21 seconds and 500 milliseconds, what does that mean? Well, 21 seconds is, 1,000 times 21, so that's 21,000 plus 500 milliseconds would be 21,500 milliseconds. Or for that matter, if somebody enters 75,500 milliseconds, if all of these are entered as milliseconds, then obviously that's going to be 75 seconds and 500 milliseconds. I'm not going to go through the long process of converting this one right now, but I would have to take the 2 days, multiplied by 24 hours. That's going to give me 48 hours. I'd add in the 4 hours and I'd get 52 hours. I'd multiply that by 60 minutes in an hour, and that's going to give me some big value of minutes. I'd multiply that number of minutes times 60 seconds, and that's going to give me some huge value of seconds, and I'd multiply that by 1,000 milliseconds, and I'm going to get a really, really long value of milliseconds. The beauty of this is you don't have to do that. So when you're dealing with RS500 as an example, you're given the time bases that you can use, 1.0, 0.01 and 0.001. But you always have to enter your time, your preset time, multiplied by that time base. I don't have to do that anymore. If I want 9.5 seconds, I enter it as 9 seconds and 500 milliseconds, and I'm good to go. I do believe, though, you are limited to working with integers still. So what you can't do is I'll have to test this, but I don't believe you can enter 9.5 seconds as an example. You are still limited to putting them in as integers, but with whatever units it is that you are trying to use. All right, so timers are the same as what we've used in the past. Not much has changed. We can still use a TON timer. You will see reference to some different terminology where Siemens will call this generate on delay. What does that mean? It really means a timer on delay or an on delay timer. And their definition of this is you can use the generate on delay instruction to delay setting of the Q output by the pre-programmed duration in the preset time. So right off the bat, we can see, hey, look, I can enter the preset time as 5S, which stands for 5 seconds. I can create my timer tag. It'll give it a generic data block. So any of your box instructions coming in will get a data block title on them, but you can still tag them appropriately as you see fit. When you put the timer in, this is the spot where you'll type in TON or TOF or TONR or TP or whatever type of timer it is that you want to use. Because we're dealing with a double integer now, we're no longer dealing with just a pure integer, as noted by this maximum of 2 billion. If we're going to store or display this data somewhere, it's going to be displayed as a double memory location, so an MD10, versus if I was doing a bit, I'd be M0.0, or if I was doing in a word, I might be MW, 1, or if I was doing a double, I might be ND, 10, like I'm doing up here. So just keep in mind that the elapsed time, now it will give you an error. If you try to put an M0.0 in here, it will give you an error, and it'll try to tell you what you're doing wrong. One of the other unique things about the timers in Siemens is they actually give you this nice little Q output. And the expectation is that you're going to hook up your output directly to that Q terminal. So, if there was a bit here like an I0.0 switch, when I turn that switch on, what's going to happen is the timer is going to start counting. It's going to get to 5 seconds, and it's going to turn on the Q output, and my pump is going to turn on. It is worth noting I can also put in another rung, below this or whatever, right? I could go down here, and I could address this timer, its done bit, by calling timer _1.q and run that over to a different output if I want to as well. So it's worth noting that timer 1.q can be addressed, in a separate rung, or I can be fed directly from the timer itself. So again, on delay timer hasn't changed. 5 seconds after this rung goes true, the Q output will turn on. Another difference from Allen Bradley is that we don't have the timer timing bit. That's not a big deal. See, people get kind of concerned, oh my God, there's no timer timing bit. Well, what is the timer timing bit really? The timer timing bit is when the input is true and the output is not true. Essentially, I haven't reached my elapsed, or my elapsed time hasn't reached my preset time, right? So comparing these two, the elapsed time and the preset time, you can create that bit using logic if you want. You just have to use 2 bits instead of 1. It's just not pre-built for you. All right, the TOF timer, or the generate off delay timer. You use the generate off delay instruction to delay resetting of the Q output by the pre-programmed duration in the preset time. So again, this is a 5-second time. Now, the most misunderstood, right? So if I call this my in or my enable, this is the most misunderstood timer, regardless of PLC platform that you're using. So I have a 0 and a 1 condition on my input. So there's a switch here or something that I'm going to turn on, right? So when that switch goes true, it's worth remembering what happens when that switch goes true to the Q bit. We'll call this the done bit, the Q bit. When we're talking about an off delay timer, remember it's delaying turning off. The done bit goes true immediately when the input is enabled. And what happens with the done bit on an off delay is when the input or the enable goes low, that's the point at which I start timing. And I time for whatever that preset time is. So I'm really delaying turning the output off. I'm not delaying turning it on. The on is going to turn on, the Q bit's going to turn on immediately with the input. If I go back to the on delay, the way the on delay works is your input goes true, and then your output waits 5 seconds. So this is when it starts timing. This is your time delay. It's on the on side. And then when your output goes low, when your input goes low, your output goes low immediately, right? The off delay is opposite of that, meaning that when my input goes high, boom, my done bit turns on immediately. When my input goes low, I delay resetting that Q output by whatever that time t is, which again is associated with the preset time, and I'm comparing that elapsed time to the preset time. Again, the Q output can be fed directly, or if I wanted to, I could have timer 1 .q in a different rung on a bit. Okay, so on delay and off delay. The TONR, so a lot of times we would call this retentive on delay in most other PLC platforms. Siemens likes to address this in their literature as a time accumulator, and it actually kind of makes sense when you think about it. Time accumulator instruction is used to accumulate time values within a period set by the preset time parameter. So if I have an input here, let's say a switch, that goes true. But let's say it doesn't go true long enough to get to 5 seconds. What's going to happen is my input goes true, and let's say it only went true for 2 seconds. What's going to happen is that elapsed time is going to be maintained. So elapsed time went from 0 to 2, and it stays at 2. And it waits there until the next time that that input goes high. When that input goes high again, it's going to start counting 3, 4, 5, and then it's going to turn on its done bit as soon as it reaches its preset time. So the done bit Q is going to turn on way over here. So what's the difference? Well, of course, the difference is the time is maintained. When you talk about an on delay timer, anytime my input were to go false, my lapse time, my output, everything would zero out. When we're talking about the time accumulator, I can have several sequences or pulses that are going to allow this thing to accumulate. The elapsed time is never going to reset. And once the done bit turns on, the done bit is never going to reset unless I make this reset pin true. So I actually have a separate reset instruction on the box itself that allows me to reset both the accumulated value and the done bit. Now, I will warn people, not just in the world of Siemens, but I will warn people in the world of all PLCs. You know, some people like to do things like use a move instruction, right? They want to move a value, move a 0 into a timer, right? So maybe you have a box instruction where you move a 0 to a timer. That's great. That will zero out the accumulated time. It won't always zero out the done bit. So be really careful. I tell people just to stay away from using move instructions with the accumulated values and with the done bits of timers and counters. Instead, use a reset instruction, and in the case of Siemens, they include that reset instruction right on the box its instruction itself. So you've got a number of different ways you can get at this thing. The time pulse, or the generate pulse. You can use the generate pulse instruction to set the Q output for a programmed duration. So this is kind of nice. So if I make the input true, the output is going to turn on for 5 seconds. So this is different, right? I'm not delaying turning on. I'm not delaying turning off. What I'm doing is I'm saying, okay, you made the enable true, right? I want to turn on the output when the enable goes true, but I want the output to just stay on for 5 seconds. This is going to, once I turn on, it's going to be kind of regardless of what happens with the input. We're going to pulse this thing on for 5 seconds. I treat it like, you know, wouldn't it be nice if when you're going to bed, you walk into the bedroom, you turn your light switch on, the light turns on, you climb into bed, you get your covers on, you do all that stuff, you're ready to fall asleep, and it automatically turns itself off 30 seconds later or something like that. So it gives you a good way to give yourself a pulse, you know, a known duration pulse, really regardless of what this input is doing right here. All right, so your S7 1200 counters. So we're moving away from timers and moving into counters now. As we get into the counters, you know, the counters that we have are very similar to the ones we've been using up till now. You know, we can do a count up, a count down, an up-down count. We can do all these different things. One of the big differences, though, is that we can define the counter data type. So right underneath the counter style, you'll see this int. Or usually it'll be these question marks, right? Question mark, question mark, question mark with a drop down. That's kind of telling you, hey, you better click on this and pick one of these. And so I can pick, well, hey, I want an integer, I want a short, I want a double integer, you know, or I want a unsigned short or an unsigned integer or an unsigned double integer. And what that means is you're really defining what the range of that counter is. And I like this. I like this because the reason why I like this is, you know, in the world of timers, we don't ever time into the negative values. So we would never be concerned about having the ability to use negative numbers. But in the world of counters, that's not always true. There may be times that we want to know if there's a negative count, right? Maybe I have a target, you know, a target of a number of items that are supposed to be in a queue of some sort here, right? And my target is, you know, 10 of these things, right? And so here's my mark, and I can be plus 10 or I can, you know, be minus 10 from that target point, right? So I can keep a value of, oh, you know, I'm 5 below where I want to be, or I'm 5 above where I want to be. You know, and in that case, I might want to use the signed integer, which is going to give me a range of -128 to +127. If that's not the case, like let's say we're the number of cars in a parking ramp, right? Let's say I have a parking ramp that holds 250 cars. I don't have a negative number of cars that could be in the parking ramp. So in that case, I might use the unsigned short integer. So there's different data types that you can select based upon how you're going to use that particular counter. And again, you can go all the way up. If you use an unsigned double, You can go all the way up to 4.3 billion. So that's a huge number if you need it. So not only can you decide if you're going to use plus or minus, you can also decide how much memory do I really want to tie up for this thing based upon how high would I ever need to count. Maybe I want to have a cap out, at 255 or whatever that number is. But you are limited by the data types shown here. So an up counter, very similar to what we've done in the RS500 platform. You can use the count up instruction to increment the value at the output CV. The counter value is incremented each time a positive edge is detected until it reaches the high limit for the data type specified at the output CV. So a couple things. We've got our preset value, and then we have our counter value here. And then I've defined my data type as an integer. I did not define it as an unsigned integer. So as a signed integer, I'm going to be negative 32,768 to positive 32,767 is what this one's going to be. And so the maximum this counter could go to would be positive 32,767. However, it's probably never going to get there, right? Because it appears the way that I'm using this particular sensor is every time this particular counter is every time this sensor goes true, my counter value goes up 0, 1, 2, 3, and so on. And then once I get to the preset value, my done bit here will turn on, and I will turn on whatever outputs associated with that. I also can attach, just like I did with the timer, I also can have a counter address on a bit somewhere, counter.q, or whatever the tag is associated with this. So in this case, it would be upcounter.q. But very easy just to tag that right to or tie it right to the Q output. Anytime I want to reset that counter, that reset instruction is included right on the box instruction there. So I have a separate switch that I'm going to use to reset this particular counter. The CTD counter, use the count down instruction to decrement the value at the CV. So this now is going to go down. Each time a positive signal is detected, the counter value is decremented until it reaches the low limit of the data type. So in this time, the negative 32,768 would be my low limit, and my high limit would still be positive 32,767. So in this case, every time I go up here, I'm going to count down. But I can also, instead of looking at a preset value, this PV on the count up, what you'll notice now is I now have what's called a load value. So load value takes this and plugs it in to my current value. So then I start counting down from 100. Okay, and then I can do things with that data as I move on. So I've got to count up, I've got to count down. And then, of course, like we did in RS500, where we use two different counters tagged to the same address, Siemens does that a little differently as well. They actually include a CTUD, which is an up-down counter. So I can see what I can do here is I can say, oh, this particular input is going to cause the counter to count up. This particular input is going to cause the counter to count down. This particular input is going to cause the counter to reset. And then I have my preset value, and I have my value here as well. So what you'll see here is my preset value. If my counter value gets to the point where it's greater than or equal to my preset value, at that point I'm then going to turn on the Q output that's up here. All right. And then a reset instruction. I talk about this at this point because it's a little different than what we may have done in previous PLC platforms, is you could use the reset output instruction to reset the signal state of a specified operand to 0. So in this particular, I'm resetting Q00 to 0. Maybe somewhere up here I've got a set of Q0.0 that I'm turning it on, and this one I'm turning it off. The instruction is only executed if the result of the logic operation at the input of the coil is a 1. So I got to make this true to make the reset instruction go. I will tell you though, when it comes to counters, we typically use the reset pin, this guy right here, when we're resetting counters in the worlds of Siemens. All right, the one-shot positive edge transition. So you'll see this positive edge transition right here. And I like this for a number of things. The first thing that the positive edge transition can do when I'm dealing with a counter is sometimes you can get a signal that's noisy, where it's really only one pulse, but that one pulse goes from 0 to 1, and instead of being a nice true, you get some noise on the line. better off to maybe shield the cable or find out why you're getting the noise. But another thing you can do is you can actually put a positive edge transition here. And what that means, I will only get one 0 to 1 transition for each scan cycle. That being said, though, let me get that out of there. That being said, though, the real big benefit of this is the positive edge transition happens. The count up is going to happen on a 0 to 1 transition. What that positive edge means is, in this case, I've got like a reflector, or I've got a diffuse sensor, I've got something. I might want the leading edge of a box or the trailing edge of a box to determine when this is going to happen. So I don't actually like using this sensor as my example. Let's say that this is a diffuse mode that's bouncing right off the box and back, right? So when it's just going out, I'm not seeing anything. But on the leading edge of that box, this sensor is going to make a 0 to 1 transition. I could do a positive edge to get a count. However, if I wanted to get it on the trailing edge of that box, I then would use a negative edge transition. So this one here would be the positive edge transition, and this one here would be the negative edge transition. What that means is if the sensor is working in such a way that I'm looking for light to reflect off the box and back to the sensor, or if I've got a metal can coming down and I have an inductive proximity sensor or something like that, as soon as it detects the box, that's the point at which I've made a 0 to 1 transition. That's a positive edge. Add a 1 all the way through the box, and then when I get to the trailing edge of the box, I go from from a 1 down to a 0. That would be a negative edge transition, where I'm doing it based upon a 1 to 0 transition. So you can use positive edge transition to ensure there's been a 0 to 1 transition from the previous scan. So this will count on the leading edge of that box. Now you got to be careful. If I'm using this reflector here, it's a little bit different, right? Because the sensor perhaps is true all the time until the box breaks the beam. But a lot of times you'll have normally open and normally closed contacts on these sensors as well. So, but just know 0 to 1 transition, positive edge, 1 to 0 transition, negative edge. And that can help you to determine where that box is on a conveyor belt. Like if I wanted to, and I see that the conveyor belt's actually going this way. I was kind of assuming it was going that way. Let's say I wanted to do it on the front edge of this box, a 0 to 1 transition, right? So that I would make sure that the box stopped there. If I did it on the negative edge, a box might fall right off the end of the conveyor belt. So lots of applications where that positive and negative edge transition can come in handy. All right, so that should take care of us for right now for timers and counters. I think the next one we'll work on here will be our math and compare instructions.